So in this lecture, I will continue the topic how to find limit point of a set. And in earlier lecture, we have seen that limit point of the set 1 by n, where n belongs to natural number or n belongs to z, is 0. And we have seen that no real numbers, how to discard that no real numbers other than 0 is the limit point of the set 1 by n. So let us look at other examples. So let me share the screen. Yes. So question from, I am going to discuss the question from this book. Question is, find the derived set. Find the derived set of each of the following. In this, first one is open interval 1 to infinity. Second one, minus infinity to minus 1, open interval minus infinity to minus 1. Third one is the set consisting of elements of the type 1 plus minus 1 raised to the power n by n, where n belongs to natural number. Fourth one, set consisting numbers of the form r root 2, where r belongs to rational. And the fifth one is collection of all those elements of the type a plus 1 by n, where a belongs to r and n belongs to set of natural number. So we know that derived set is basically collection of all the limit point of the set. So to find derived set, we need to look at the limit point of the set. So let us discuss this first one. So given set, let me call this set as A is equal to open interval 1 to infinity. We need to find its limit point. So we already know that the criteria for that definition demand that suppose S is any given subset of R, then we claim that L is limit point of S, F is limit point of the set S, if for every epsilon greater than 0, if for every epsilon greater than 0, L minus epsilon, L plus epsilon, that is every neighborhood of L, its intersection with the set S other than L is non-empty. So this one is the requirement for any real number L to be limit point. And here remember that L belongs to R. So limit point can be the member of the set, can be out from outside the set. So we need to check all real numbers. So to verify that, so we will see that its limit point, basically its derived set is going to be 1 to infinity. So how to do this? So here we have this definition stands for that if every neighborhood of L intersect with S infinitely, then L is said to be limit point of the set S. Or if every neighborhood of L, I mean for each epsilon greater than 0, if every neighborhood of L, its intersection with the set S other than L is non-empty, then we say that L is limit point of the set S. And to discard, one need to show that there exists at least one neighborhood of L which is not following this definition. So to discard, one need to construct at least one. We have seen in previous example or this example, which I have discussed earlier, of the type that 1 by n belonging to n, we have seen that its limit point is 0. If I call this set as B, then B dash is 0. So just go through that lecture, you'll find the idea that how to find a limit point of a set. Now I am going to discuss this one. So to show that, my claim is that here, that limit point of this set A is equal to 1 to infinity. The derived set is going to be 1 to infinity. So we need to check what we will do that suppose L is any real number, because we know that for limit point L belonging to R, here we have two choices for this set, whether L belongs to A or L belongs to R minus A. So we need to look at every real number L from the set and L outside this number. So if L is less than 1, so what will happen if L is less than 1? So if L is if any real number less than 1 is not a limit point, so we need to construct at least one neighborhood of L, this arbitrary L which is less than 1, whose intersection with this set A is empty. So how we will do that? So let me draw this. Suppose this one is 1, here we have infinity, and here we have any real number L less than 1. L less than 1. So just measure this distance. What will be this distance from here? It will be mod of 1 minus x. Obviously 1 is greater than 1 minus L, because I have taken this number as L. So this is mod of 1 minus L. This distance is mod of 1 minus L. Now if we choose neighborhood of L, that is L minus epsilon, L plus epsilon, in such a way its intersection with say 1 to infinity, its intersection with the set 1 to infinity for this epsilon. Just take any epsilon lying between this distance 0 less than epsilon less than mod of 1 minus L. If we choose any epsilon, then what will happen that this set, the intersection of this set, that is L minus epsilon, L plus epsilon, where epsilon is less than mod 1 minus L, this will not going to intersect this, the shaded portion here. Let me shade it with some different color. Its intersection with this one is clearly empty. So for this epsilon, because definition demands that it should intersect with every neighborhood of L, means for every epsilon greater than 0. But here we have constructed a neighborhood of L whose intersection with this set, with the given set A, is non-empty. Here no need to write singleton L, because singleton L, I mean apart from this L, because L is less than 1, so it is not going to be part of this one. So clearly this one is empty. So for this epsilon, for this particular epsilon, it is clear that this we have constructed this neighborhood whose intersection with open interval 1 to infinity is empty. So this shows that no real number less than 1 is going to be its limit. Now what about L is equal to 1? What about L is equal to 1? Is this a limit point? So to show that L is equal to 1 is the limit point, let us construct this one is 1 infinity, and we need to show that this one is its limit point. So whatever neighborhood we choose for L, 1 minus epsilon, 1 plus epsilon, its intersection with the open interval 1 to infinity, 1 minus epsilon, 1 plus epsilon, this is going to be non-empty. This is going to be non-empty because 1 plus epsilon, 1 minus epsilon. So this portion is going to intersect. It will contain infinite members from this set A. So this is the reason why this set L is equal to 1 is going to be its limit point. So one can write here that L is equal to, one can write here that, let me write here. So that if x belongs to, in fact not only for x equal to, for L is equal to 1, in fact if we choose L belonging to 1 to infinity, then one can observe here that if the set, given set is 1 to infinity, I mean the set A, and whatever L we consider from this one, suppose L is somewhere, L is greater than 1 or L equal to 1, we have already seen that this is going to be limit point. Now if L is greater than 1, then again whatever neighborhood we consider this for neighborhood of L minus epsilon, L plus epsilon, it's going to intersect with the given set A. There lies infinite members from the set from this set A is equal to open interval 1 to infinity. So this is the reason why any real number L including 1 and L greater than equal to 1 is going to be its limit point. So one can write that if x belongs to this 1 to infinity, then for every epsilon greater than 0, this x minus epsilon, x plus epsilon, its intersection contains infinitely many members from the set A. So this is the reason why. So what will be derived set of the set A? So derived set of A is equal to 1 to, sorry, derived set of this open interval 1 infinity to A is equal to closed interval 1 to infinity. Now let us look at some other examples. Similarly, the other case of the second example is what will be the derived set of minus infinity to minus 1. So let me call it as B. So one earlier to just what we did in the example 1, one can verify here that it's the derived set will be here minus infinity to minus 1 closed at minus 1. We need to show, actually the set C is this one, 0 union 2 by n, where n belongs to set of natural number. So our claim is that its limit point is 0. 0 is the limit point of C. 0 is limit point of the set C. So to claim this, we need to show that for every epsilon greater than 0, the neighborhood 0 minus epsilon, 0 plus epsilon, its intersection with the set C apart from 0 should be non-empty. So I am going to claim that from Archimedean property of R, this will contain infinitely many members of the type 2 by n. And already in C, we have the members of the type 2 by n. So its intersection is going to be non-empty. That is, in the intersection, it will contain infinitely many members of the type 2 by n. So to claim this, that it will contain just take help from Archimedean property of real numbers. That for every epsilon greater than 0, there exists a not belonging to set of natural numbers such that 1 by n is less than epsilon, 1 by n is less than epsilon for every n greater than equal to n naught. And if you multiply here, one can also write into this form. Actually, this is since epsilon is greater than 0, or one can also say that just multiply it by 2 by n less than 2 epsilon and call this as epsilon dash. So just rewrite the statement here in place of epsilon, just write it as epsilon dash. So for every epsilon dash greater than 0, there exists n not belonging to n such that 1 by n is less than epsilon dash. I mean, in between 0 and this epsilon dash, there lies infinitely many members of the type 2 by n. So for this epsilon dash, for every epsilon dash greater than 0, because epsilon is greater than 0, so 2 into epsilon is again greater than 0, and this epsilon is arbitrary. So one can rewrite this statement as that every neighborhood of every neighborhood of 0 will contain infinitely many members of the type 2 by n. So this claim comes from Archimedean property of real number. This statement that NA is greater than B. That if B is any if A and B are any positive real numbers, then there will exist n such that NA is greater than B. So using this, one can show that in between 0 and this say epsilon, here just write it as 2 by n less than epsilon. So in place of a, just take a is equal to epsilon and b is equal to 2. So if we take this, then we have n times epsilon is greater than 2. So here we have 2 by n. This implies that 2 by n is less than epsilon. So either use this, that if a and b are, if a for a greater than 0, b greater than 0, uh, we will always get a natural number n such that n times a is greater than b. So in that one, if we take a is equal to epsilon and b is equal to 2, then we always have this one. Or one can also claim in this way. So this shows that, and similarly one can claim that no members other than 0, I mean no real numbers less than 0 or greater than 0 is its limit point. So just use the same logic what we have, what I have discussed in for this set. S is equal to 1 by n, where n belongs to set of natural number. So using that, one can discard that no real number apart from 0 is going to be its limit point. Now the third is fourth one. Fourth one is show that find the derived set of this one. S is equal to R root 2. R root 2 where R belongs to set of rational number. So we will see that its derived set is whole R. Its derived set is whole R. Means whatever real number we will take, every real number is its limit point, or every real number is going to be limit point of this set. This means for every epsilon greater than 0, whatever real number we choose, then for every neighborhood of this L, it is going to contain infinite members of the type this S minus L. Its intersection with the set S other than L is going to be non-empty. This we need to claim. So again, this can be done using the density of these rational numbers. We know that rational numbers are dense in R. T closer is R. So using that, let me explain how to show that. So suppose L is any real number. Let L belongs to R. Then for each epsilon greater than 0, L minus epsilon and L plus epsilon. This is going to be neighborhood of L. Is going to be neighborhood of the real number L. So and obviously here L minus epsilon is less than L plus epsilon. This implies L minus epsilon, or just divide by root 2 on both sides. So this is also L plus epsilon less than L plus epsilon by root 2, and just use the result. Since between any two distinct real numbers there lies infinitely many rational numbers, therefore there exist infinitely many rational numbers R such that, so just use this statement that between any two distinct real numbers, between any two distinct real numbers there lies infinitely many rational numbers say R such that this L minus epsilon by root 2 is less than, say R is less than L plus epsilon by root 2. So in this interval, in every neighborhood of L, there lies infinitely many rational numbers. From here, so this implies that on cross multiplying, I can write here that L minus epsilon is less than R root 2 is less than L plus epsilon. So one can see from here that every neighborhood of this L, that is L minus epsilon, L plus epsilon here, will contain infinitely many members from this set of the type R root 2. So it will contain this one is containing the members of this type R root 2, and already in set S we have the elements of the type R root 2. So this is the reason why its intersection is non-empty. So this is due to this, because L is arbitrary, so one can see that its derived set is whole order. That is, every real number is going to be its limit. So using this denseness property, this set is going to be its limit. The derived set of this set is going to be whole order. Similarly, for the next example, the fifth one, here it's given, we need to find the derived set of this one, a plus 1 by n, where a belongs to R and n belongs to a. So this question is actually similar to if we put n is equal to 1, we have a plus 1, a plus 1 by 2, a plus 1 by 3, and so on. So this one actually, this question is similar to, we have already seen that for the set S is equal to 1 by n, for the set S is equal to 1 by n, where n belongs to n, its derived set is 0. Its derived set is 0. That is, 0 is the only limit point. So in that we have seen from Archimedean property of R that whatever neighborhood we construct for 0, 0 minus epsilon, 0 plus epsilon, it is going to contain infinite members of the type 1 by n, and and its intersection with the set S, with the set, is going to be non-empty. So just shift this 1 by n type members in the neighborhood of 0. In every, suppose we have 0 here, so in every neighborhood of 0, that is 0 minus epsilon, 0 plus epsilon, we have infinite members. We have infinite members of the type 1 by n. That comes from Archimedean property of real numbers. So just shift 0 to a. So again here, directly from Archimedean property of real number, one can say that if every neighborhood of 0, that is 0 minus epsilon, 0 plus epsilon, contains infinite members of the type 1 by n, and let us shift this 0 to a. So what will happen, that a plus 1 by n, a plus 1 by n, and every neighborhood of a, that is a minus 1 by n to a plus 1 by n, this will contains infinitely many members of the type a. So let me rewrite that every neighborhood of, for every epsilon greater than 0, that is for every neighborhood of a minus epsilon, a plus epsilon, this will contains infinitely many members of the type a plus 1 by n for n belonging to n. So one can directly claim here, because if every neighborhood of 0 contains infinitely many elements of the type 1 by n, so just add a to just translate this interval by a, so it will contains infinitely many elements of the set S equal to a plus 1 by n. So this is the reason why a is going to be its limit point, because in every neighborhood of a, it will contain infinitely many members from the set S. So this is the reason why its derived set will be singleton. Derived set will be singleton. And parallel to that earlier question of this 1 by n, one can discard that no real number greater than 1 will be its limit point, no real number less than a will be its limit point. So same logic one can use here. So for objective, one can directly see that using the Archimedean property of R, one can always find some n naught belonging to n, such that 1 by n is less than epsilon for every n greater than equal to n naught, n naught. So what will happen, that if we add a plus 1 by n here, then it will be have a plus, so for every n greater than equal to n naught. I mean, this means that in every neighborhood of a, that is in between 0 and epsilon, we have the members of the type a plus 1 by n from this set for infinitely many values of n. In fact, countably infinite values of n greater than equal to n naught. So this is the reason that in every neighborhood of 0, we have infinitely many members of the type a plus 1 by n. So it is going to contain infinitely many members of the type a plus 1 by n, and its intersection with the set is always non-empty. Thus, its derived set is A only. Derived set is A. And in continuation to this, there is another example. Take it as home assignment. I will discuss it next time. This one is also again from our median property of real number. This is also from the book by N.P. Bali. Just go through this example. Question is that prove that the set of limit points of the set A is equal to 1 by P plus 1 by Q, where PQ belongs to N, is B is equal to 0 union members of the type 1 by Q, where Q belongs to N. Where Q belongs to N. So set of all limit point. We need to show that set of limit points, that the derived set is this one. Set of limit points and derived set is this one B. So again here one need to use the Archimedean property of real number. So take it as home assignment. See, from Archimedean property of real numbers, in every neighborhood of 0 we have infinitely many members of the type 1 by P, or just replace P by N, because P here we have taken notation P belongs to N. So that, and again there will be infinitely many members of the type 1 by Q. So that will help you to show that every neighborhood of 0 will contain infinitely many members of the type 1 by B plus 1 by Q from the set A. And again, if you, not only this, in fact, because every real number 1 by Q, every real number 1 of the type 1 by Q is also going to be its limit point. So that claim will also, that we will also claim from, that we will also claim from Archimedean property of real numbers. Okay, so look at its proof. We need to show that the set of limit points of this set 1 by P plus 1 by Q for PQ belonging to set of natural number is B is equal to 0 union 1 by Q, where Q belongs to set of natural number. So first we will show that 0 is its limit point, and then again we will show that not only 0, in fact every member of the type 1 by Q is also its limit point. So for the proof, actually all these proofs depend on Archimedean property of real numbers. So in first case, because we know that the limit point L or X, whatever notation we choose, if we need to check all members from this set A as well as X from outside A for limit point. So let us discard that no real number less than 0, because its already answer is given here that 0 and elements of the type real numbers of the type 1 by Q is going to be its limit point. So we need to, and this one is positive and this one is 0 here, so no real number less than 0 is its limit point. So let us discard for first that no real number less than 0 is its limit point. So case first here is that if X is less than 0, then what will happen, that we need to, because we need to discard that no real number X less than 0 is its limit point, no real number less than X is its limit point. So we need to construct at least one neighborhood of X whose intersection with the set A other than the member X is empty. So let us consider this arbitrary neighborhood of X minus epsilon, X plus epsilon for epsilon greater than 0. So this one is a neighborhood of X, and this neighborhood will contain negative real numbers, and the set A contains positive real numbers. So the intersection of this X minus epsilon to 0 with the set A minus X is empty, clearly empty. However, X is not in A. This will, because this contains negative real numbers, and this will contain positive real numbers. So clearly its intersection is empty. So this is the reason why no real number less than X is its limit point. Just wait. So we have seen that no negative real number is limit point for this set A. Now let me discuss case second here. How to case second. Set is given by A is equal to 1 by P plus 1 by Q, where PQ belongs to natural number. So in case second, now from Archimedean property of R, we will see that X equal to 0 is going to be its limit point. So again, we already know that for every epsilon greater than 0, every neighborhood of 0 will contain infinitely many. Our purpose is to show that every neighborhood of 0 will contain infinitely many members of the type 1 by P plus 1 by Q. This is the reason why its intersection with set A is going to be non-empty. Now, how to show that every neighborhood of 0 will contain infinitely many members of the set of the type 1 by P plus 1 by Q? So that comes from Archimedean property of R. So let me write it. We know that from Archimedean property of R, for every epsilon greater than 0, one can there exists M naught. There exists say M naught, or in fact one can choose this P also. For every epsilon greater than 0, there exists P belonging to N, such that just write it. There exists M naught belonging to N, such that 1 by P is less than epsilon for every P greater than equal to this M naught, for every P greater than equal to M naught. Now, if now for all Q greater than equal to P, for all Q greater than equal to P, since it holds for all P greater than equal to M naught, so obviously for all Q greater than equal to P, we can it can be also claimed that 1 by P, that if Q is greater than equal to P, then 1 by Q will be less than equal to 1 by P. So if 1 by P is less than epsilon, then obviously 1 by Q will be less than epsilon. So I can say that 1 by Q plus 1 by P, 1 by Q plus 1 by P is less than 2 epsilon. And let me call this 2 epsilon as epsilon dash. So just rewrite the statement that for every epsilon dash greater than 0, in between 0 and 2 epsilon or 0 and epsilon dash, there lies infinitely many members of the type 1 by Q plus 1 by P. Or in some books you will find that they here start with epsilon by 2, and epsilon by 2 plus epsilon by 2, they call it as epsilon. So either you denote epsilon plus epsilon as 2 epsilon or epsilon dash, it will not matter, because epsilon is greater than 0, and so again epsilon by 2 will be greater than 0, and since epsilon is arbitrary, so from Archimedean property of R, whatever neighborhood we choose for 0, whatever epsilon dash, so I can say here that for every epsilon dash greater than 0, for every epsilon dash greater than 0, 0 minus epsilon dash, 0 plus epsilon dash, 0 plus epsilon dash will contain infinitely many members of the set A, of the set, that is its intersection is non-empty, because in between 0 and epsilon dash, we have seen that there lies infinitely many members of the type 1 by Q plus 1 by P, 1 by Q plus 1 by P, and already this type of members are also present in set A, so this intersection is going to be non-empty. So this is the reason why 0 is also going to be its limit point. Case third. So in case second, let me write the final statement that every neighborhood, what we have observed here, that every neighborhood of 0, that is minus epsilon dash of 0 contains infinitely many members of the type 1 by p plus 1 by q from the set A, and this for every q greater than equal to p of A. But remember that this claim comes from Archimedean property of real numbers. So this implies that 0 belongs to A dash. This implies that 0 belongs to A dash. Now next case is that to show that case third, to show that not only this but in fact all the members of the type 1 by q will be also its limit point where q belongs to n, where q belongs to n. So again this can be claimed from Archimedean property of real number that for every epsilon greater than 0, for every epsilon greater than 0 there exists m naught belonging to set of natural number such that 1 by p is less than epsilon, so that 1 by p is less than epsilon for every p greater than equal to this m. This implies that minus epsilon is less than minus 1 by p for every p greater than equal to m naught. So in general, I can say that 1 by q minus epsilon, 1 by q minus epsilon is less than 1 by q minus 1 by p. Just add 1 by q to both sides of this equation because 1 by q is a non-negative real number. And this is less than 1 by q, 1 by p plus 1 by q, 1 by p because 1 for p greater than equal to q. For so this one is basically less than 1 by q because from 1 by q we are subtracting a positive real number 1 by p. So this is going to be less than 1 by q. Or I can say that 1 by it, this is less than 1 by q plus 1 by p because 1 by p is a positive real number, or and because 1 by p is less than epsilon, just we have seen from Archimedean property of real number that for 1 by q is this 1 by q plus 1 by p is less than 1 by q plus epsilon because 1 by p is already less than epsilon. 1 by p here is already less than epsilon, so I can replace this 1 by p by epsilon here. So what I am trying to construct here, that in between every neighborhood of 1 by q, that is 1 by q minus epsilon and 1 by q plus epsilon, there lies infinitely many members of the type 1 by q plus 1 by p. So that we have that every neighborhood of 1 by q, that is 1 by q minus epsilon, 1 by q plus epsilon for every epsilon greater than 0, every neighborhood of 1 by q, its intersection with the set A minus 1 by q is going to be non-empty because A also already contains elements of the type 1 by p plus 1 by q, and here we have proved that 1 by q every neighborhood of 1 by q, that is 1 by q minus epsilon 1 by q plus epsilon, will contain infinitely many members of the type 1 by q plus 1 by p. So this intersection is going to be non-empty. So this is the reason why every x of the type 1 by q is going to be its limit point. Similarly, one can discard. So this implies that every neighborhood of 1 by q, that is 1 by q minus epsilon, 1 by q plus epsilon of 1 by q contains infinitely many members of the type 1 by p plus 1 by q for every p greater than equal to say m naught of A. So this implies that 1 by q belongs to the derived set A dash for every q belonging to set of natural number. Similarly, one can discard that that other real numbers lying in between 0 to 1 or greater than 1 will not be its limit point. I mean, where x is not equal to q, 1 by q. I mean, except all other real numbers apart from 1 by q is not going to be its limit point. And in fact, for x greater than 1, again, those real numbers cannot be limit point. So what I have discussed earlier, using the same logic, one can discard that these the real numbers x lying in between 0 to 1, where x is not equal to 1 by q, is not its limit point.